So yeah, I'm Tanya Manager from the I'm the project manager for managing background leakage. I believe we are a transformation 2 project, so we've been going a while now. Our project's split into 5 phases. A, B, and part of C is now finished, so we've completed our field work and we're just doing our analytics in phase B. Phase D is where we are looking at our calculation. And then the last phase, phase E, is about project dissemination, sharing our results, and doing our final report. So yeah, we are probably about 3/4 way through. In our so yeah, Westwater are one of 5 water companies. We've got 7 Portsmouth Water, Amazon Water, and Filton Water within the project. And then we've also got Menio, HWM, and University of Sheffield within our project. We've also worked with other contractors over the period of time to deliver the field work, so they are all partners. But yeah, as I was saying, Transformation 2 took a budget of about 2.8 million and 2.3 came from the Ofwat-funded. Really excited in 3 years. I came on board slightly afterwards, but yes, really exciting. Right, and the team are here later on to talk to you about what we have done within the project. That's pretty good. Design alignment. Okay.
So not but for I'm pleased with the relation to your together and obviously about design alignment. And I think I've been with this project now for almost 5 years. The campus to then comes forward. The idea of design aligner, I'll give you a quick introduction, and I'm going to hand over later to the people doing the doing in the project. I'm going to say it's a designing a lining solution fit for 21st century water network. So if you think historically, we've procured lining solutions, we've bought solutions that have been provided to us by the supply chain. This is about designing from scratch or adapting what we already have and trying to overcome some of the barriers we have in the lining market, regulation, testing, and bittering cost. So far, we've had about £3.6 million from the Ofwat Innovation Fund. Sounds like a lot of money, but when you see some of the amazing technical work that has been delivered today by really new entrants to water, it's quite incredible. We're going to talk more about some of the benefits that lining will bring, and Leah will talk about that later. But if you've never seen a pipeline before, it's an incredible way to rehabilitate a network by minimising customer disruption, reducing costs, reducing carbon. And we want to see if we can take that to the next level and find even further benefits. And we're going to talk about some really exciting material science developments today. And ultimately, the solution that we're going to deliver to get near market. I would encourage you to come and see some of our demo kit today. We're going to have a go at showing you some bits in the presentation. But please do go and talk to colleagues on the stand. A lot of them are very new to water. They've only been working in a couple of years, but their passion for doing something amazing, material science, to get this lining solutions market really is incredible. So who are our partners? Because you always should flash up some logos. So we are privileged to have great water company support, some really good technical insight into the project that really challenges us. Our new entrants really to water are the National Composite Centre and the Bristol Composites Institute, so that's the University of Bristol. And I will tell you that this interaction came about because I had a chat with a gentleman in a coffee queue at Utility Week Live. So if that wasn't encouragement today to talk to somebody you don't know about things you don't know, great things can come. So I'd really encourage you to move out of your comfort zone. And we're always grateful to have our domain expertise from WRC Water Research Centre and Tetra Tech RPS that really bring that technical rigour and upskilling, particularly the colleagues, to what we're doing today. We are now at the stage where we're looking for industry partners and we're working through that process. That is why there's no supply chain logo up there. Designing from scratch, not picking a partner first, and making sure we're designing a lining solution that really fits the needs of our customers. So what do I want you to take away from today? I really want you to think about how lining could fit into your business and water company. At the moment, this is challenging. Some of the regulations put in place by Ofwat make that difficult. But I want you to think beyond this, how might it have benefits? And I'd also really like you to have a think about how you might bring new sector entrants into your work going forward as well. So we have a lot to learn and share, and we've started to do some of that sharing with projects like the No Dig projects from Thames Water, and to learn and share some of this expertise about how we bring those new entrants in successfully, upskill and develop. So they're really the two things I'd like you to take away today. How can we use lining well? And learn from us about bringing in those new entrants. We really are open to questions and comments. Line can be a bit contentious. Hopefully you'll get some discussion going in the group exercise. It's really a privilege to come and talk to you today. Thanks very much.
Morning everybody. So my name's Alan Brown. I'm from Northumbrian Water, and some of Carl said this morning, Carl number one, what Carl covers. I talked about the value of team, and I think this project is an example of that. And just to kind of back something Katrina just said there, this project actually came out just by myself and John Gaffney meeting at an exhibition stand at a conference around service reservoirs. And it turned out we had a very similar philosophy, what we wanted to achieve. John's passion and work, and something I kind of wanted to do for water quality place. And we actually brought Sheffield University on board. They kind of had they were invested in the philosophy as well, and from that we kind of created a really strong team from that. So what was that goal? What was the philosophy? Very simple. We have a lot of online instrumentation at our treatment works. You know, we have using that process control at every stage of the treatment process, and we can almost monitor every single drop of water as it goes through. But then it goes into the network, and apart from things like flow pressure, we have very little. We're almost reliant on the customer telling us if it's gone wrong, or compliance data giving us an indicator that something might not be right. So that was essentially it. How can we create real-time indicators within the network so we can improve customer service and improve customer confidence along that as well? Now, there is two key elements to that ambition, because what we didn't want to do is just put one or two discrete analyzers in a network. That will give you some nice data, but it doesn't tell you a story. If we were going to do this, we needed to do it at scale. Yeah. So what we need to do is be able to tell that story equally, but that scale had to give us some value. It had to have a payback. So they were the kind of the red lines, if you like, that this project had to deliver against. And we'll go back one. So yes, we got Ofwat innovation funding to try and do this, and we had a number of partner organisations that helped us with it, including the number within the water sector as well as dissemination partners. So in terms of what this deployment looked like, we picked Teesside. That is from Teesdale area near Barden Castle, going through Darlington, Middlesbrough, Scotland, all the way to East Cleveland, basically to the border, our border with Yorkshire Water. We put multi-parameter sensors on the inlet and outlet of all the reservoirs in series within that network. We put those same multi-parameter sensors on the inlet of DMAs. We added in sample data that we were already collecting. We also put in high-frequency pressure sensors to then put a different angle. It wasn't just water quality focus, it's what extra insight we could pull from that. And also we could bring in SCADA data as well. Why did we pick Teesside? We knew we had some high profile events in that area. We'd had discoloration issues, we'd had taste odor issues. So there was a burning platform from our perspective. And what we were trying to do from this is, you know, if you take discoloration as an example, customer rings up, says, water deteriorated. What happens is we respond to that. Yeah, we might go and flush their network. We'll take some samples, etc. But it's very much about finding what that root cause is. What we're trying to do with this is to almost get some high resolution data that allows us to understand, for example, the mass balance of material as it accumulates and moves around the network. And then from that, we can almost get to this diagnostic stage instead of being reactive, where we can almost validate what we're doing, you know, and understanding why that contact has occurred. The next stage, and this is where we kind of ultimately want to take it, is to get into that predictive stage. So it's not just understanding the accumulation movement, it's how and where that that material will move. And from that, we can put just-in-time maintenance in place, so we can proactively flush DMAs before that contact comes in, as an example. That ultimately gets us to a point where, you know, we are improving the service to customers on a much more consistent basis. So that's and the team will go through the information around that. But again, you know, this has been a fantastic team effort, and I think that's the thing that I would stress. It seems like this case across all of these projects. So I think everybody kind of keep that in mind. Great, thank you.
But just a quick background for those of you who don't. So research in the run-up to the 2018 price review found that water companies haven't yet developed the cultural mechanisms required for the most effective innovation. There wasn't a lot of collaboration going on. There was limited knowledge sharing, sort of data sharing. Innovation was happening, but not really to the extent it was needed to tackle some of the sort of big challenges of that step change that we. So some incentives for innovation were introduced in the PR19, and one of these was the Innovation Fund. So at the moment, it's a £600 million fund over 10 years to stimulate innovation in the water sector. Central objective being to enable the sector through innovation to better meet the needs of and create long-term value for customers, society, and the environment. And there's two ways we go about doing this. The first is to fund the innovation projects in the sector. That's end-to-end conceptualization all the way to rollout. And the second is everything that goes around that. So in order to build that ecosystem of sustainable innovation, so that's the capacity building, the culture change, everything that sits around the project. So on that first strand then, most of you know about the competitions. These projects will all be funded through the first is Water Breakthrough Challenge, a flagship competition, water company led. These are generally all very collaborative projects, innovation sector, etc. There's two streams in here: Catalyst, which is projects from 150k to 2 million, and Transform, which covers bids from 2 million up to 10 million. And this competition is open at the moment. Catalyst was in January. Then in response to feedback from the sector, the Water Discovery Challenge was launched. This is a competition for earlier stage innovations aimed at sort of innovation-led projects. So water companies can enter. There's no 10% contribution or IP restrictions. The money involved is a lot less, so companies can get up to 500k to develop their projects, plus they then get a package of financial support, non-financial support, from water companies, which includes sort of mentoring, business development, sort of bit of embedment in the sector. And we'll be running 2 rounds of that in the next out, and the next one will in late January. So the space for that. So through these competitions, we've awarded just over 200 million so far to 109 projects, covering all elements of the water cycle over the last 5 years. And I've just thrown this graphic up here to illustrate the sort of breadth of the projects that we're supporting, from urban catchments all the way down to resource recovery and circularity, all sorts of projects, tech projects, ways of working, sort of new methods of collaboration. The whole works really very broad. So we doubled the fund for AMP8, which means we now have 400 million to allocate over the next 5 years. And with this increase in value, we will also be increasing the scope and the ambition of the programme. Continue to fund projects, continue with Water Breakthrough Challenge, Water Discovery Challenge, increasing the funding available to both streams. And we will also launch 3 new work streams. We have in the process of developing and launching these at the moment. So we've got the Water Innovation Missions, which is about bringing water companies together to collaborate on solutions to the sort of specific sector-wide strategic challenges. We've got the implementation program, which is about identifying and addressing the barriers to scale the rollout of our projects and other innovations. And then we've got the cross-sector challenge, which is about working with the sectors that water touches, all the water adjacent sectors, and thinking about how we can jointly support and jointly find solutions to shared problems. And I'll spend the rest of this brief introduction just talking a bit about those more details, because we've got some exciting new updates to do. So the cross-sector challenge, and we've also got some nice new logos, which you can enjoy. So the cross-sector challenge, we know that water touches everything, interfaces with several other sectors, whether that's agriculture, energy, highways. There are countless shared challenges that water sector cannot address on its own. So the cross-sector fund is about connecting with and developing new ways of working with these other sectors to identify some of the shared challenges and look at how we can deliver
sort of mutually beneficial solutions to society. It'll be £40 million over 5 years, and we'll be looking to fund projects as part of that as well, ideally with joint funding for other sectors. We're currently working to identify priority sectors for engagement. As part of this, we created the cross-sector water innovation network, which is essentially sort of community for organisations and individuals from across the water sector and adjacent sectors to sort of align their efforts and explore how they can sort of build cross-sector partnerships to address these shared problems. So sort of hub for events, communications, knowledge sharing, where people can just sort of get together. So you're all welcome to sign up. The link is here. I think these slides will be shared at the end. All sign up to that. That's future hand. Our second new work stream is the implementation programme. So this stems from the sort of basic premise that we can fund as many successful pilots as we like, but we need to see these scaled and rolled out across the sector of impact that we want this funding to have. And we know there's all sorts of barriers to that. So this again is fortunately over the next 5 years to identify barriers to implementation, address them, and then in doing so accelerate the deployment of the funding. The next bit is actually very, very new news. We just announced what this will look like. So we know the programme needs to do two things. It needs to enable individual projects and it needs to tackle sector-wide barriers. We've got the two complementary streams that will hopefully do that. So the early adopter and fast follower stream, this is a stream that will provide 50-50 match funding for water companies to implement proven innovations at scale. So 50% total project costs funded by the fund, the remaining 50% funded by the company. And this sort of co-funding approach is intended to ensure that the applicant has significant commitment and skin in the game required, which we have been told that is critical for a successful adoption. To get this funding though, at least 2 fast followers must opt into all associates. So the early adopter will complete the first implementation. It will do the knowledge sharing, it will share lessons learned, and it will share practice support with the fast follower cohort, which will then implement the same solution in front of organisation. So this is designed to sort of demonstrate repeatability and just accelerate adoption and ensure greater value of our innovations. The second stream then is the implementation enabler stream, and this is essentially to address the broader barriers that hold back innovation across the sector, the adoption of innovation across the sector. So that's data sharing challenges, capability gaps, cultural blockers, anything that makes it harder for these new ideas and new innovations to move from demonstration to this stream is going to operate a series of sprints. End-to-end sprints, each designed to address a single barrier each, and bringing together a committee that will identify priority barriers in the sector. We did our first sprint as part of the National Innovation Festival, looking at the barriers caused by Regulation 31. So stay tuned again for updates on that. Of that. The last of our 3 network streams sadly doesn't have a staggered logo yet, but is the Water Innovation Missions, formerly called the Collaborative Challenge. So basically, through competitions, they're highly collaborative, and we've seen great partnerships between water companies and with water companies and other sector organisations. But there's still that competitive element. They're still competing with other bids for us. This work stream is designed to be fully collaborative, mission-led, and bring the sector together to collaborate on the solutions to strategic pre-identified challenges. So there's the big, ambitious, complex issues that are too big maybe for 1 or 2 organisations to solve by themselves and might require progress against multiple barriers. We're currently researching possible challenges within that sector. Some front runners so far, and again, these are PFAS and emerging contaminants will be to maybe build some of the work that Spring will be doing. Bioresources, scaling nature-based solutions, that's big sector-wide challenge.
Explain how you do the project, trying to explain why it's ridiculous. So I'm going to start by giving a bit of background what the project is about. This is a graph from the Ofwat website, but it shows the trend in leakage since the early 1990s. So going back to 1992, we had 5,000 megalitres a day of leakage in Wales. And then during the 1990s, it dropped. I left the water company in 1994. And you can see this big reduction. I'd like to take credit for that. I'm not joking, really. I actually went round all the water companies, helping them to set their economic level of leakage. And then we got lucky. We had a big drought in the mid-1990s and leakage targets were set. And the water companies then started eating into a backlog. So they've been a long time. And my country helped them to do that. From around about year 2000, things flattened out. And we've had round about 3,000 megalitres a day of leakage right up until 2017, 18, going into this AMP effectively. The plan now, these are the target, the commitments that the industry is giving, triple under rate of leakage reduction from 2019 levels by 2030, a 37% reduction in leakage by 2038. And then this one, the big one, halving leakage from 2017-18 levels by 2050. I'm going to come back to that slide. What is background leakage? Leakage isn't leakage. There are different breeds of leakage. Okay, we have what we call reported leaks. These are leaks that come to the surface. People see them and they ring at the water company saying you've got a leak. That only accounts for about 10% of total leakage because those leaks don't run for very long. We then have the unreported leaks, which we can find, but we have to go looking for them. And then we have, once we've cleared reported leaks and unreported leaks out of a district meter area, I'm going to talk about DMAs. A DMA is a district meter area. It's a sector of the network that is metered through a district meter and it's valved off to a discrete area. Once we've cleared these leaks out of an area, we're left with this background leakage. So what we have, management curve diagram, visible leakage, non-visible leakage, and then what we think is leakage. It looks like leakage. It's defined in the leakage route map as the level of leakage below which we can't go with current technology. We can alter it by replacing pipes in the network. I'm not sure about that. Not convinced at all. Or by reducing pressure, definitely by reducing pressure. And through technological innovation, some of which we'll hear about today. The way we measure background leakage is through what we call MAL, the minimum achieved level of leakage in a DMA. So every district meter area has a minimum achieved level of leakage. And if we add all those minimum achieved levels up, we get the background leakage for that area or that company. The first thing we did in the project was look at the data from the 5 participating water companies. This report has been available for a while now through this big share thing. It's a 31-page report, and in summary, it shows that 49% of what the water companies report as leakage is this background leakage in DMAs. 31% is the unreported leakage, 5% is reported leakage, and 15% is trunk main and service road reservoir leakage on straight to the DMAs. So 50%, if I go back to this, if 50% of this leakage is background leakage, how are we going to halve leakage by 2050? It means we have to get rid of all of these other forms of leakage completely and just be left with that 50%. That's how the project started. So is it achievable? Is 50% reduction achievable? It can only be achieved by eating into this level of background leakage. So instead of thinking of the minimum achieved level as just a single type of leakage, we produced this diagram in the project which says the first thing is it leakage or is it not leakage? And we found that some of what's being reported as leakage is not leakage. It is night use, which is higher than what the company estimates. It's internal plumbing loss within houses, which is higher than what the company estimated. And there are metering and hydraulic events. Where it is leakage, it can either be growing leaks, small leaks which are growing, which will be found. It could be the undetectable background leakage as currently defined, or it could be hidden leaks that have run for a long time, which can be found if you look hard enough with the right technology. And the project set out to find these hidden detectable leaks. So when we go into an area, a district meter area, the first thing we do is a desk study. is that the DMA suitable? But we look at the maps, we look at all of the information around it, we look at the initial leakage level, the burst history and so on, we say, does that DMA look suitable for this sort of investigation? Then we send a team in, they spend a couple of days in there looking at things like, are there any traffic concerns? In some cases, they have actually found leaks when they go in to do the survey. Are there any potential breaches of the area? Various things over here. And then what sort of area is it? Can we get access to the stop taps? Do we need to clean out chambers and so on and so forth? So when we first started the project, we would just send a team in the area to do the full logging survey. And we found that that wasn't working very well. So we now do this soft survey. When we do go into the area, what we're doing is we're blitzing the area with sensors, with the aim of producing an all connections network model of each DMA and having a consumption profile for each connection at high resolution. And we do that using our stopwatch technology, which Tom's going to talk about. We model the consumption profile, again, using stopwatch. We've looked at the paradigm data from a company called SME. I don't know if there's anyone here today who's familiar with that, but we built that into the equation as well. We fit pressure loggers to every available hydrant. We fit in transient loggers at 100 Hertz frequency, and we've had to develop new techniques within HWM to do that, and also to analyze and store that vast amount of data. We install acoustic loggers, and again, we've got new techniques on acoustic analysis. We combine those data sets and we identify areas of interest within the DNA where these hidden leaks might be occurring. That's the top. Good.
You can go to about. Morning, everyone. Hello, my name is Tom Alps. I'm a data scientist working for HWM. If you haven't heard of HWM, we're a manufacturing company based in Cwmbran, which is just north of Wales. And we've been providing the instrumentation for managing background leakage projects. So today I'll be talking about one of the technologies that is kind of a cornerstone of the project, which is Stopwatch, which Stuart alluded to. And also some of the data management and the data platforms we're using. And I'll hand over to Rich from the University of Sheffield who'll talk about the analysis and the results we've been getting from the project. Okay, so Stopwatch. What's a stopwatch? Fundamentally, it's a very sensitive logger with a emitter attached to it, which you can attach to a customer stop tap. And we have some unique algorithms which we can use to analyze this temperature data to give an estimate of flow. It's a way of estimating flow, finding leakage. We can find very small leaks with this method as well on stop taps that don't have a meter, can't be fixed with a meter. And as Stuart mentioned, as part of the background leakage project, we have basically flooded these DMAs with stopwatch loggers. And we also build up this connections hydraulic model of the network that University of Sheffield have been doing. So you can see in this photograph, this is just so you get a visual. The top photograph is a mister attached to someone's stop tap, so this is where the data get measured from. We can measure to 1/500th of degree Celsius, so they're extremely precise measurements. And the photograph below is the logger which the mister attached to. We have two algorithms that we use to analyze data from Stopwatch. The first is called continuous flow analysis. It's the machine learning model, which we have trained based on thousands and thousands of examples of leaks with temperature data. And what we'll do is we'll deploy a logger for a period of a few days up to a couple of weeks. We analyze the data, and the machine learning model can then estimate is it a leak, or is there not a leak? And if there is a leak, we'll come up with an estimate of the size of the leak. And you see the slide here, we have three categories. Small leak is below 10 litres per hour, medium 10 to 60 litres per hour. Large is anything over 60 litres per hour. We will then provide an estimate of the flow rates from the machine learning algorithm at 1-minute intervals to the data warehouse, which the University of Sheffield are then putting into their analysis. We also report any leaks identified by Stopwatch to the water company for their follow-ups. Our second algorithm is called intermittent flow analysis. So we're not looking for leaks for this analysis method, but we are looking for consumption that is non-continuous. It's based on physical principles about relating to flow and temperature. And again, it enables us to provide at a high resolution, so 1 minute, we've been using this project, estimates of a flow rate for a stop tap. It's not a meter, it's a statistical method, but I think some of the results can speak for themselves. So, following two slides, giving examples of where we've used these analysis and the temperature data, just so you can get an idea of kind of that it actually does work. Here is a kind of profile of temperature recorded on the stop tap where we've identified a small leak. So if anyone's familiar with sort of pressure graphs, you know that there's you might see a dip in the morning and a dip in the evening. Well, temperature does a very similar thing. It's very strongly related to how the age of water in the network. So along the patterns we look for when we identify leaks. So you can kind of see this. We've got about 7 days here where there's we're measuring these 2 dips in the morning and the evening. And basically the machine learning algorithm picks up these patterns and it's identified as a leak that's less than 10 litres per hour. We were able to confirm the water company through their smart metering. Most of the deployments we had for the project, they weren't very smart meters, but this one did, and we confirmed it was a 2 litres per hour leak. So it's very, very sensitive to even very small leaks. Here's an example of stopwatch being applied to a stop tap where the customer doesn't have a leak, but they do have usage. So what you're seeing here is our various drops in temperature over what's about 3 days. So what happens when someone uses water is the water in the mains is at a different temperature from the water that's resting in the stop tap. As soon as they turn on the tap, the water in their stop tap will change temperature very rapidly, and that's where you see these drops. So the water temperature in the mains is going to be cooler than the ambient temperature of the water in the stop tap. You can see every time there's a drop in the temperature, we're identifying a flow at the same time. So this is an example of what the data looks like, which we're finding as inputs for the hydraulic analysis that Sheffield are doing. I'm now going to briefly talk about how we're managing the data for this project. So there's a lot of data coming from different sources. We, as Stuart mentioned, we request a lot of data from water companies, so historic data, static data, and DMO flow meter data. This slide goes over the data flow process for the field data that HWM are collecting from our instruments. Step 1 is a DMA survey. So what will happen is technicians will go out into the DMA, identify all the places where we could deploy a pressure logger, an acoustic logger, a temperature logger, survey all customers' stop taps, decide whether they need to be cleaned out or not, and we deploy a logger there. And we'll also conduct, we have for the phase C of the project, we've also been doing sounding of stop taps with the HWM's DX mic. So step 2 is we'll deploy the loggers and we use a deployment app called DataWatch Collect, which interfaces with one of HWM's cloud platforms, DataWatch, to record metadata and deployment information about the loggers. So the logs will then be left out for a period of at least a week. Then retrieved, and we collect that data by the same app. Then we download the data. Some of the loggers need to be downloaded manually. Some of them we access the data from HWM systems via API. HWM do our own analysis on the data, which is the stopwatch analysis on the previous slide, where we estimate continuous flow and intermittent flow. And all this data is then uploaded for each DMA to a central data warehouse, which is the relational database, which Sheffield University have been accessed data via. So this slide just briefly goes over what our data warehouse is. As I mentioned, it's a relational database containing temperature data, acoustic data, pressure logging, metadata, pressure data, acoustic data, stopwatch data. So all the data from the instruments and the DNAs. We update it at the end of the one period for every DMA, so there's 25 DMAs in the projects. It all looks now completed. So the data warehouse is now, for all intents and purposes, complete and full. The graph on the top right shows the data that we're collecting and proportions of data in the data warehouse. You can see over 75% of it is actually this 100 alerts past volume data. It's actually one of the big challenges of the project in how we deal with this data, and also some engineering developments that we use to enable the multi-log LX loggers, which are one of the HW impression loggers, to record this data and to get the data off the loggers again as well. So the point of the data warehouse was data integrity. We're combining data from multiple different sources, and we have one data model for all the deployments, which allows us to efficiently query the data all in one place. Okay, so I'm going to hand over to Rich now from the Sheffield to will talk about the results and the research.
Thanks so much. I have just giggled. I made them do that data storage where I just make them store all that data, and I'm actually going to talk about it today. So, that first has been really exciting, really interesting, but I've only got about 2 minutes now, I think, for it to finish. So I'm not actually going to chance to talk about the parts of the project that we've done. So we're going to focus on a couple of things that we've done with some of the data that was collected as part of the project. And I believe we've got a bigger full dissemination later when we talk about the outcomes of the project. So, I'm responsible for the University of Sheffield. Been working.
Sweet, my cable.
Okay.
Bear with me, I should.
So I'm from the University of Sheffield. I'm working alongside with. Oh, we've got 10 minutes. Oh, fantastic! A bit more. I'm working alongside Joby, who I'm sure most of you will know, on the manufacturing project, as well as a couple of colleagues, Tom, or Ed, and Mohammed Ali, who have been doing most of the actual work on the project, and I've just been seeing that background. You've seen the slide before. Obviously, we're collecting lots of different sources of data with this project. And basically what we've been asked to do at the Sheffield was try and collect some of this information together and process it in a way which will allow us to identify what background leakage there might exist in the networks we've been exploring, and potentially also then identify where that background leakage is actually occurring. Obviously, that's the whole idea, of being able to find it and allow water companies then to go out and fix those pipes, which they previously haven't been able to identify what the leakage was. The first challenge, though, is obviously really to work out what actually is background leakage and where is the. We know we have a significant amount of water coming out of the networks, but where is that water actually going? How much of it is actually authorised usage going to customers that we don't appreciate how much water they might be using at night? How much of that is coming through customers' meters, but then being lost from customer meters, so on that customer side leakage? And how much of it is genuine network leakage for the water utilities who have a responsibility to go out there and find and fix? So this is analysis that we've been doing using the stopwatch meter data that has been collected as part of this project, alongside the DMA flow meter data that we've had access to from various water companies, and also the hydraulic models that we've been provided by the water companies we've been working with. So what we've been trying to do is basically understand all of the different sources of meter data we have access to. So here we're using stopwatch as our smart meter, which is allowing us to identify between customer continuous usage, so leakage from customer households, plus then any of the intermittent profiles that Tom talked about before a second ago. We then want to try and sum all that up together and try and scale it to appropriate for how much we think isn't actually measured, but we know about in the network, and then attribute whatever's left over to unaccounted for water, which we then distribute to either unmeasured customer side leakage or possible network side leakage. The two elements of that that's really quite important for us is that we need to have enough measurements of stopwatch in the network to be able to get a good customer profile pattern for that DMA, and hope that it matches the DMA profile pattern reasonably well. If we're happy and we're confident to do that, which you can kind of see in this plot here. So this green line down here is actually the summation of all of the stopwatch measured data from this network. So whilst we were trying to get as high a level of customer meters or customer measurements in the networks as possible, in most situations with the complexities of installing this technology, we only got to a maximum of about 70% customer coverage. So even with all the stopwatch meters we've collected, we don't get every customer measured. So what we've had then is this green line at the bottom is the actual measurements we've taken. We have then factored that up to account for customers that weren't measured. So we've just basically taken a broad assessment of how many customers were measured, how many weren't, to allow us to work out what we think that should be. And if then that is a good pattern match with the DMA in the flow meter data, we then take the hypothesis that the majority of the variation that we see in the DMA in the flow meter data is attributed to customers, and therefore we can scale the customer measurements that we've got to account for the same variability in the customer measurements, the same variability we see in the DMA measurements. That allows us to give us the best estimate we have of what actual customer usage that we have in the network. We can then subtract from the DMA in the flow meter the scale customer measurements we've got to allow us what servers left over. With stopwatch, we get an idea of the continuous flow rates in the networks. That's the orange line here. So we can subtract that from our calculation, and then whatever's left over is unaccounted for water in that DMA. So that gives us an idea of actually how much of the network of water coming through your DMA flow meter that isn't going to, we don't know where it's going to. Then, based on the idea of how much we can scale the continuous flow measurements we had with the rest of the customers that weren't measured, we can get an idea of how much of the DMA, or how much of the unaccounted for water was potentially customer-side leaks, which we didn't measure, and how much then is possible network-side leakage that we need to account for in our network. So this is then the graph. This is my key results slide. Then we've got all the different DMAs we were back to. So this is how that broke down for all the different DMAs we were looking at. So a few things that you can see here. So there's quite a lot of variability in the night flow levels. So the size of the graph is basically the size of the night flow in each of these DMAs. Now a bit of that obviously is attributed to the different sizes of DMAs. So this is in these per second, so it's an absolute measurement of the amount of flow. But obviously it's quite clear that the green bar here, which is the customer usage at night, that varies quite a lot as well. How much customer-side leakage was measured, again, there's a big variability between different networks. And then the unaccounted for water that we actually have in each of these networks, again, is the blue bars, which is then split into the light blue, which is the network-side leakage, and the dark blue, which is the potential customer-side leakage. So if you're going out and looking for different, which DMAs you might want to be focusing on, just taking the night line level doesn't necessarily tell you very much about actually how much network leakage that you might be looking to try and find. Just taking these two as an example here. So one label here is A6 and one label here is B2. They have almost exactly the same night line level. They have very different customer usage. A6 also includes some large industrial users, some separately metered customers. And actually, the network side leakage that we've found for these two networks, one of them has about 0.1 litres per second of predicted network side leakage, so very, very small, whereas the other one is about 0.5 litres per second in terms of network leakage. So 5 times different predicted network side leakage, even though they're having the same absolute night line level that we've seen tested. So what we're getting to that then is that even with a relatively small amount of measurements of customers, and both of these probably in about 30% customer metering, that we've got a very different understanding of what's actually going on inside your network in terms of the leakage profile of each of these different DMAs for a very similar night line level. So that's kind of highlighting for us, really highlighted the value of actually taking customer measurements. I mean, it feels fairly self-intuitive, but actually, actually measuring what customers are using gives us a much better idea of what's actually happening in the network. So just understanding the big variability in what customer night line use is, understanding the variability in the customer leakage profile is a big step forward for us in terms of understanding how much of the network of the leakage that we think we've got is actually background leakage, and how much of that is potentially not network leakage that we have to try and find. Once we've done this, again, I put the slide in, probably we'll skip over it quite quickly, really have time, but this is the same graph but has proportions of the amount of network leakage. So again, you can see that the amount of network side leakage in some of these DMAs was almost 50%, and some of them it was basically zero. So the different DMAs have a really big difference in terms of what I project. But obviously that was in the first part. Once we've identified roughly what the network leakage we're trying to find is, then obviously the task is try and find it. So what we've been doing then is combining the stopwatch data that we've been collecting with the pressure data that's been also pressure at the same time, to try and build a hydraulic model which allows us to identify where anomalies between the measurements and our hydraulic model are to identify where there's potential for network side leakage. So again, we're building these all connections models, so we're trying to model every single consumer because we now have profiles for the majority of the consumers, and we're infilling with synthetic profiles where we don't have that data. And then it allows us to, as I say, make a comparison between the day and night flows of the system and the day and night pressure drops around the system to identify where we find a similar pattern in our model compared to what we actually see in the real system. Again, this isn't a massive step forward. It's something that's been done before. The real key advantage that we've been able to show with this project is, though, when again you have actual measurements of customer data, which are happening concurrently with the pressure measurements, you can get significantly better results in terms of where you have anomalies in your hydraulic model compared to the pressure measurements when you've got some sort of assumed customer demand, but you've got very little or you're higher certainty on what customers are actually doing at any given point in time. So again, this is one of the methods we were looking at. So what we're looking at, the patterns that you have here, this is the measured system response, and this is our best fitting model that matches that system response. And that identifies the areas in red at the extremes of this network is where we are identifying significant anomalies between the model and the real system, which is where we attribute that to potential leakage in that system. Okay, very quickly, my last slide then. Looking at the acoustic side of things as well. So again, acoustic data is one of the key tools that we have been using this project, but also as water industry use acoustics to find leaks a lot. In the project, we've been trying to implement one of the advances that come out of the University of Sheffield a few years back, which is looking at trying to extract more information from our leak signals to identify not just the amount of energy in the signal to identify where its leak is, but effectively its frequency pattern, which is described here as the short time crossing rate. Which allows us to separate leaks from non-leak signals in this sort of two-dimensional plane now, rather than just looking at the energy in the signal, say when is there enough noise in the signal to say it's a leak. Now we're saying is when is it enough noise and it's got a certain frequency pattern which suggests that it is not a background flow or it's not sort of external noise like generated from the surface, rainfall, something else we've got to see messing up our leak acoustics. And it allows us to very clearly distinguish away different sort of leakage much more clearly with this two-dimensional sort of vector space. And that's been, again, implemented out through the management of that leakage project has been quite useful because we've piloted a lot more potential leaks and quite a few times piloted where we thought leaks were, but don't actually look like leaks. We've tried them this project. So I think that's where I'm going to stop. The next thing then, is the more actual results we presented at the next event that will be in about 3 or 4 months' time, something like that. So this has sort of been meant to give an overview of what we are doing, and later on we'll show you how it's all worked out. I think that's me.
You to take away from this, if you take nothing else away, that lining is relevant to the water industry at the moment, and we'll see. I'll talk about it in a minute. It's got a long history. Some of the new science and some of the engineering that we'll present is really interesting and has the potential to change lining and maybe your perception of lining from the past. And also, we're a bit of an imposter here because we're halfway through our programme. We're not near the end, so there's plenty of barriers. You'll hear me talk about barriers, but we've got some really exciting things to show you and talk about it. And there are some really exciting solutions, and the project will go on. This is the team. So Katrina showed this earlier. I just wanted to make the point that this project, like some of these other Ofwat projects, has brought together a team that have never worked together, a number of individuals who have never worked in the water industry. They're bringing in quite disruptive ideas, which are challenging us in terms of what they're thinking about. But in terms of lining, which is not new, it's really changing our perception and the way we look at these sort of solutions. So it's important, I think, in these really challenging problems that we bring together teams that bring different expertise in. Is that going to wake itself up?
Sure.
Yes.
Yeah, sorry.
Yeah, that's right. So why lining? And I won't dwell on this. Everybody in the room knows of the scale of the challenge with our asset base ageing asset base and all of the associated problems with that, and the reality that we cannot replace that asset base quickly enough. So therefore, lining is a viable solution. And this is where Design and Lining project comes in. So lining, it's a potentially attractive solution, but actually, if you look at the market at the minute, the products that are available, relatively limited number of products, there is a gap between what those products are achieving, what they can deliver, and what we need in the 21st century, what the water industry needs as a solution. There has also been a specific challenge around lining as a rehabilitation technique. If it is to be compared and judged against other techniques, whether they are the rehabilitation techniques or replacement techniques, it needs to have an extended life. And we need to be able to give confidence to the industry that that lining technique has an extended life of, say, 50 years. And that hasn't been available. I've put here the lining market is at a standstill. I've used quite a strong word, paralysed by regulation. That lining is almost at the centre of regulation coming from all different regulators, which is basically trying to kill lining at the minute. This project is, as well as developing technology, developing a solution, is trying to reinvigorate lining, raise lining, the profile, and help water companies and regulators and supply chains engage in solving those sorts of problems. Because I think these regulations have not been put in place deliberately, but as a result of those regulations, we are seeing challenges in implementing what are potentially viable technologies. I will move on. So we all know why we rehabilitate pipes. The point I wanted to make here is that this is not something new. This picture is probably from the 90s. It's really old, but this is not a new thing. In the same way, lining is not a new thing. I quite like this cartoon. And lining has established benefits over replaceable. We know that lining is cheaper, it's quicker, it's better for the environment, to reduce customer impact. And we know that for water companies, that speed and that customer impact within a constrained AMP cycle can actually mean that the benefits of lining, the benefits we have, can be achieved sooner. And that's a big positive within that cycle. So I wanted to take a step back, and I said I'd talk a little bit broadly about lining. This project has been considering two types of lining: spray on lining and cured in place type lining. And I'll talk a bit about those techniques in a minute, but there is a history to these. We are not talking about stuff that is new to the industry. The 1980s and 1990s for spray lining, and that's the blobs along the top, the orange ones. This was the boom period for spray lining, and some of the individuals in the room were around then, and they know about the development of the epoxies and polymer type linings. And those technologies, they were used on a wide scale. We had 50 contractors with vans out delivering really wide scale use of those techniques. So these are two different technologies that we'll be looking at in the project. So let's talk a little bit about each of those. This is Yorkshire Water last AMP working with Morrison's spray lining. They did 9 kilometres or so of spray lining, working with Morrison's. This is the before and after picture, very well characterised. You can see, and I think they demonstrated through what could be considered quite a modest actual scheme. They actually demonstrated that it was cheaper, reduced carbon. They could spend less time on site compared with replacement. One of the key benefits, I think, which we mustn't forget, is that actually with a spray lining approach, actually there's a safety element. So you're not digging as many holes, you're not digging as much machinery, you're not lifting and moving plants around so much as that. There's a safety element to that as well. I wanted to talk a little bit about SIP as well, because this is probably the technology that people are less familiar with. And it comes in lots of different varieties and lots of different colours, even green. Not sure how well that's going to go down with the water industry, but anyway. So predominantly SIP is used in wastewater, and we know it best for wastewater. This photograph in the middle is like 10 years ago. WRC helped to transfer SIP from wastewater to the gas industry. Gas industry hadn't used it before. Gas industry is very, very safety conscious, but this is now being used in London for gas mains to London. So there is a big challenge with SIP as a cured in place system. And Sophie will talk a bit about how it's produced, but it covers any connections or any joints. So you have to go back in and you have to remake the connections, unlike spray lining. So there are some challenges with that. Back to sort of lining and some of the barriers to new lining solutions. And we have created as an industry a lot of barriers to new entrants to this market. I pick up a few of these. So regulation, we've got various different regulations. Our regulations around customer minutes loss and the 3-hour rule, they don't prevent us doing lining, but they do make it difficult for you to do lining. It's not helpful. Regulation 31 has been talked about to death, and I won't talk about it anymore, but as a new entrant to this market, that is a big barrier. And then more recently, the price control measures have not been very favourable on lining in terms of the definitions, and they have put a bit of a barrier on lining, at least in this angle. There's also cost is a big barrier. So as somebody who wants to bring a solution into the UK, we like trials, we've got lots of regulations. We're not a particularly attractive market to lining at the minute. And we're not very ambitious or good at presenting that UK market to new people who might be coming want to get into the UK. And finally, testing. Yeah, all sorts of testing. I think the testing bit that I wanted to mention in terms of barriers is if we're talking about extending the life of lining, there's a whole load more testing around extending the life and demonstrating that that asset can be rehabilitated and can be compared like for like with a replacement or another rehab technique. And that's quite complicated, and that's quite a barrier to new lining solutions. So lots of barriers, but, and I said before, Yorkshire Water, Morrison's Water Services, Morrison's achieved approved contractor status, the first company for a long time to have been through that process and trained and approved contractors, and they delivered work in Yorkshire Water, which was successful. So we can do it, and we can do it with existing technologies. The question is, for designer liner, what do we as a project need to impact? And I'm repeating myself a little bit, but this long life and this confidence in this extended asset life is really, 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 really important. That and this customer benefit. So it's about cost-effective solution and limited disruption or no environmental impact. I think this fourth point on this slide is really important because it's talking about the willingness and the skills as an industry to work together. That's a slightly softer thing that the project is trying to do, is raise the bar and say that regulator, water company, supply chain, let's work together to solve some of these challenges. Individually, you're not going to solve. So I'll delve a little bit more into the project. So as Katrina probably said earlier, this has been quite a long running programme of work. It was a first phase catalyst stream project, and now we're in the middle of a second phase of transformation stream project. We're about in the middle. So, and the project is all about developing a 21st century lining solution. So not just tinkering or tweaking with what's previously been done, but actually looking at the 21st century, what is needed for the industry now. So we're right in the middle of our programme at the minute, bang center in the middle. So we have done work looking at what are the requirements. Let's forget about existing technologies. what are the real requirements that the water industry has in terms of rehabilitating pipes? And what are the fundamental material solutions that can help us address those? And we've been looking at things like the cost benefit. So if we bring in new solutions, for example, and Ben will talk about it in a minute, a self-healing material, how does that change the cost benefit analysis of that approach? And that's quite challenging to work that out. And if you bring in those sorts of materials, how do you test those? Because the appropriate methods you've got at the minute are not suitable. So you need to develop new testing programs and new ways to work. So we've got lots more of the program to deliver. And I think today was about updating you and telling you where we are and showing you some of the exciting things that we've been up to. We've done quite a lot of work on refining and cost benefit. We could do a whole presentation on this, but I'm not. And actually, I'm not going to talk about the detail of the slide. I think the cost benefit stuff is about two things. The first bit is making the solution cost effective compared to alternatives. So demonstrating that we can get that cost effective solution. And what that means is that water companies can do more with the pot of money they've got. It's not about doing less, spending less money. It's about delivering more, because if we go back to the beginning, size of the challenge is almost unachievable in terms of the network. So the more we can do for the pot of money that's available, the better. And the second part of this cost benefit is around understanding those materials that we are developing within the project and understanding what materials can we use and how much can we spend on those materials and those processes compared to the benefits that can be achieved. We've got people in the team who are working on advanced composite carbon fibre in other sectors, and that cannot be directly transferred to the water industry. We're never going to have carbon fibre pipes. We need to balance that cost benefit with the benefits that the water industry will achieve. Talked quite a lot, so I'm going to hand over to Ben, who's going to delve a bit deeper and talk about some of the technologies, a bit more science. Over to you, Ben.
I'm Ben. I am from CC, research engineer. It's new concepts that I'm currently working on to do the sign program. Concept one is based on a straight-line technology. With what design liner bring to this concept through tapping agents, test tube with various that you sprinkle into your resin that apply. The two things that it's going to add is a tapping element, tapping element, which our theory of pipe to a little bit stronger than its original form to allow it to last a few years longer. What we are currently proving now is that the base epoxy, by having its base epoxy has increased in strength for the properties. The next stage we're working towards is then doing a lifetime test to go base epoxy or this one. These tapping agents we've demonstrated making us a bit longer. The second element is a healing agent. It's a triggered healing element. So essentially, when that sort of cracks start to form in this spray lines, heats will be sent down the pipe. This will then heal cracks. Again, pipe. Our second concept is based on cure and place. The innovations that Slang Liner is bringing to this is also the resonant and the tapping agents. It's a sort of can be resin, polymer, epoxy, etc. Add that to it. An additional thing we can bring to it is using braid. Just a second, but essentially braid is going to help reinforce corners. So those 22 are used 45 investigating some of their here. In theory, forms easier to go around bends. There's less reworking to get them on imperfections. It also has that structural element as well down to the fact that it's a SIP method, very much limited to bridging defects, something that's very likely is limited to. So the whole technology together, we have a longer, stronger survivability material solution. How the life extension theory going to work? Pipe, identified through various means, and then send the heat will be down that pipe, that crack, then in theory heals, doesn't need to be relined, doesn't need to duff up, is contained within that membrane. It just theory just has to solve that. These two slides are a demonstration of thermally triggered epoxy. On top you've got crack, as you can see, right, it's just pure without the healing element. So as you can see, the has changed. It's under a microscope as well, so the appearance has changed. But at the bottom we've got the epoxy and the healing element. So yeah, same crack is pretty much gone. So at the moment it's still coupon level. So lab scale, we've improved it epoxy with the next stage for that is simply the aged yields. And raise, so it's a certain innovation with that to the plate. Please do consider this and have a look at it. Very interesting to have a look at it. And it probably better explains by touching it before explaining it. Essentially, it is a continuously woven, interwoven tube sock that is made out of various materials. Fibre, but we are using a glass fibre, that can be mixtures of materials from the glass mixture as well. There's tons of things we can do. We can change the open, change the pattern, do lots of things to design essentially what this thing needs to perform. The main benefit to the sleeves is the ability to be so loose. As you can see, it is very open, which allows it to, as you move it, to open and close, to conform to defects, to corners. But because it is continuous, it improves that ability to be able to withstand forces, movements. It allows it to bend and perform, and to that survivability to it. At the moment, we've got a couple of demonstrators that we're already managed to kind of do, but the next stage is that we need to do is to get bigger and start some forces and some regressions to get demonstrate that it is going to be capable of surviving what it needs to be able to do. Right, I'll say Sophie to the teaching.
I'm sure some of you already have an understanding of what some of the lighting equipment looks like, but probably most of you, when I came in with this, thought it was a computer cannon or something like that. I certainly did when I first got it. So this is what Picote supplied us. So they are a lighting company currently looking more so into the sewage water network. But we are trying to adopt the technology that's currently used in industry into water as obviously for drinking and stuff. It's like roll. That's fine. So as Ben and Leo said, we are looking at braiding using a glass fibre. So this is currently off-the-shelf material. It's braided and then using a 45-degree material angle. Obviously, as Ben said, we're going to be looking into changing that orientation to see if we can achieve a bend, which is notoriously some of the biggest challenges that we have in the water network at the moment. So we're currently quite early stages of the trials. This was our very first attempt, obviously not the best, but we are working towards amending the way that we lay up our material and amending the way that we use the equipment in order to achieve some of the requirements that the industry needs to achieve. So I just wanted to kind of give you a little brief teaser into what the equipment looks like. I will be at the table over there if you would like to come and speak to me more. I probably feel a bit nervous in front of such a big group, so I apologise for that. I promise I will be much better in a smaller group at the table. So please feel free to come and speak to us over lunch. I really appreciate it. So over to you.
Thanks, Sophie. Thank you. Just two more slides from me. So what next? As I said, we are pretty partway through the programme. And one thing that we recognised when the programme was set up, design aligners should not be about developing a concept and then at the end of the 3 years or 4 years saying, ta-da, supply chain, we've solved all the problems, just buy this and just adopt it. We recognised we needed to take them on the journey. So at the moment, we are working on a process to bring in a partner, a supply chain partner, who will engage with the project and will ensure that the technology, that's clever stuff that's being developed, actually gets through to a product stage. Because none of the people in the project at the minute are suppliers or SIP products. Alongside that, it's a lot of testing, development work and approvals. Our plan is to get to a stage where we've mirrored the Regulation 31 approval process within our project. So although the product won't have that, formally have that tick, we will have been through the process and it will give people confidence, or at least the supply chain confidence that it's achievable. And finally, this point about demonstrating lining as an even more attractive cost-effective solution, that will continue through the project. So just in terms of those takeaways that I put at the beginning, hopefully you've realised that lining has changed in the last 20 or 30 years. It's very relevant to the water industry. There's some new exciting science and engineering coming into it from other sectors, but there's still plenty of barriers and plenty of challenges for us to overcome. This wouldn't be an Ofwat innovation project if it was easy, and I think that's why we're here. There's more challenges than we will probably solve, but if we can get most of the way there, it'll be a very successful project. Thank you.
We would have thought a turbidity alarm on the first service reservoir on the network along Newton, which would have given us the opportunity, if you look at the travel times of the water, would have given us that in that window, we would have been able to intervene, cut off the service reservoir and discharge discoloured water, and that would have, while it may still have happened, we would have prevented that spread across Teesside. So that kind of gives a bit of a feel for some of the benefits we could have. So fast forward to earlier this year, we had another event. Was a different root cause this time. This is a Lyington treatment works, which is the second one, second water treatment works as part of the network in Teesdale. What happened there was more discoloured water got pushed into the network, but we were able to intercept through the use of the application, the spread of the event. And so you can see here, this is a much more local view compared to the previous map, whereby we were able to actually target specific villages to intercept, deploy the flushing teams for the peak impact, and then we put us on a more, maybe not proactive, but more diagnostic footing. Something had happened, but we're able to intercept, mitigate, and ensure that it didn't get any worse. So obviously, while we would rather that both events hadn't happened, I'm not going to canter through all the numbers here, but you'll get a bit of a feel for the first event is the without water quality analytics there. Second is the more recent one, but every number or figure or impact in that slide, in that column rather, is significantly less. 35 contacts is obviously 35 too many. We're down from 411. We had far fewer impacts on our operational teams and the customers. The amount of time it took to resolve was down to about 3 or 4 days from about a fortnight. And one of the key headlines for the business case was that for the first event, we spent something in the region of £700,000 on service reservoir tank cleans. We might avoid at least £600,000 of that. If it had been like the first event, we probably would have had a similar situation. So it was a local event. The second one, less disruption, down from a huge silver or gold event with big reputational damage. So obviously, the certain building blocks have to be in place to make that possible. For us to do that, to make sure we've got confidence in the data and we can actually intervene. So it's a number of items. One is the actual hardware, the sampling of the particulate material. Next bit is the need to real-time alarming, so you're actually getting that intel in time to do something about it, and how that works architecturally. And then obviously the business model that makes it all work, to make sure that the data we're seeing is something we're confident in, and there has to be things that underpin that. So just sort of slide on each. And the hardware that we use at the moment is the HydroClam B4, which you can see the items that it measures. Obviously turbidity is the one that we're interested in this particular example. But it's an agnostic platform. Something else comes along that's better or can improve the situation. Sims platform can adapt and be flexible to receive data from that. So part of the innovation project was to validate the performance of these meters to make sure that the info that we're getting was something that we're confident in, and also make it a fairly simplistic install. It has a purge mechanism and it suspends the correct particulates, gives a reading that can rely on rather, has an accurate timestamp so we know when it happened, and also in terms of power, we have to look at battery life and how often we dialed in to make sure that the maintenance schedules weren't too onerous, too costly. So that was the first pillar. The second one is latency in terms of getting the alarms and the alerts to the right place quickly. So it's not a big architectural oversight at this point, so please don't worry. Essentially, the data goes to the ClamNet platform, which is the sensor manufacturer's proprietary software. Comes across to Siemens. There's an element of filtering taking place in terms of business rules applied to make sure alarms aren't raised that are potentially spurious. For example, if we had an overdue maintenance job, which we shouldn't have, on a sensor, we wouldn't want to raise an alarm for that because there might not be a reading we can rely on. But it's 15-minute date to Siemens. Siemens do the filtering, and then we get the email notification services running every hour with alarms to follow, which we're doing some development work on now. So that gives us the speed to get the data quickly enough to actually be able to do something about it. And the last part is the business model. I think typically in the past, we've either had unreliable reads or difficult for water companies to keep up with the maintenance regimes, which means that, again, can you trust the data? So the model that we agreed and developed and worked on over the period of the project was that Siemens own the hardware, they run the services, they install and maintain them on agreed intervals. The data, the analytics and the service and the software is their proprietary work with some of the listeners of the Keely is going to talk about soon about the analytics. And then underpinning that, we have a service level agreement, so which has some teeth and penalties associated with it. So ensure that data quality and data availability is sufficient to make sure when that data comes in, we're confident that's right and we can intervene and it's reviewed and kept on top of on a weekly basis via a governance structure with meetings now that we're in BAU. So the water company responsibility, of course, is slightly less, but it's water quality analytics as a service. So effectively, we as Northumbrian Water pay for the data and the insight and the analytics. Obviously, we have a responsibility to make sure site access is there for supporting surveying, install maintenance, and obviously we need to make sure our users are engaged and ready to adopt. But so those are kind of three things that underpin that use case to make it possible to be something that we can trust and rely on. So that's the first one, and then I'm going to hand over to Killian.
Thanks. I'm Killian Gleeson from the University of Sheffield, and I'm going to run through some slide work we've done in this project, which has all been about developing analytics. And when we first started, we drew up a list of over 25 different analytics metrics that we thought we could potentially do in this project, and we ranked them in workshops and things for their viability and impact within this project. So I'm presenting two of the key metrics that we found, and the first one is the median daily standard deviation of turbidity. So it's a bit of a mouthful, but it's a really simple and robust metric for assessing discoloration risk using a single time turbidity time series. So it effectively tells you how much, on average, the turbidity sensor is fluctuating on a daily scale, which is in line with daily hydraulics, which we know is what dictates discoloration events. So it tells you how foul upstream pipes are, what the risk is downstream. Yeah, so when we applied this to DMA inlets, which are some key locations we have turbidity sensors on, we were able to show an agreement with customer contacts, smart customer contacts, which is usually how flushing would be decided. So this shows the promise for this metric to be used to target which DMA to flush. And then once we actually flushed the DMA, we were able to install sensors within the DMA and see what the risk levels were at 3 different locations. By installing the sensors and seeing what the metric said, we were also able to compare this to a complex network theory approach, which basically looks at which pipes are the most hydraulically active, with the idea that the least hydraulically active pipes are potentially higher risk for discoloration. So we found agreement there, and then we were able to use this metric to see which locations were most successfully flushed. So this shows how these sort of analytics could be used not only to target a DMA to flush, but also to do more targeted flushing within a DMA. We also use this metric to condition a trunk main. This plot on the top right hand side is the monthly median daily standard deviation per DMA inlet, and you can see there are several with quite elevated levels during the summer. So this was how we decided to condition a trunk main that fed into these DMAs. And we used a VCDM model, which is another University of Sheffield tool, to plan and model the flow rate and the turbidity response. And this plot shows a turbidity time series within the Siemens dashboard with several key KPIs, and the median daily standard deviation is currently being integrated into the application. The other metric is about service reservoirs. Service reservoirs were a major focus in this project. We had 10 service reservoirs with inlet and outlet water quality monitoring. So this was one of our analytics that we identified as having a strong impact on viability. The 2 plots on the right hand side are from a hackathon that we ran during the project. So the top one just shows a really strong seasonality across a historic data set of 300 reservoirs across 4 years. So basically the highest risk of bacteriological failures occur in the late summer months. And then this on the bottom right is a machine learning technique called self-organizing maps, and without going into it too far, the insight that this gives us is that there is improved chlorine residual when the service reservoir level is cycled more frequently. So this led us to focus on mixing as a analytic for these reservoirs. We came up with this metric where we basically calculate the residence time in each reservoir 2 different ways and compare it. So the first way is a standard sort of hydraulic residence time. You divide the volume by the flow. That's basically how long is the water spending in the tank on average. The second way uses the inlet-outlet water quality sensors and uses cross correlation to find the lag between them, with the idea that any big difference between these 2 residence times would be indicative of short circuiting and potentially poor mixing. We applied this to 6 of the reservoirs which had sufficient inlet-outlet data, and we were able to identify 3 with potentially poor mixing, and we were able to use regulatory sample data to verify this. We then ran a validation exercise on one of these where we had confirmed water operate the reservoir at a normal operating level and then a enhanced cycling level, and it did show an improved performance in this metric, which shows its promise. So this plot shows the amount of different data you can get together to understand what's going on in a reservoir. This is actually the reservoir that was during the validation exercise. So you can see the blue line at the top is the average level across both tanks. and you can see it's kind of stable at the start, and that does fluctuate quite a bit, although it is actually operating at a lower level too, so that complicates matters. But there is, so the red dots at the top are the water quality risk score, which is a metric derived from flow cytometry, so it does show a reduced risk during this period. But there's also increased temperature, there's changes in chlorines, there's a lot going on. So really what this shows is just how much information you can get together for one single asset in order to make more proactive, data-driven asset management decisions.
Okay, so you can see we've been through a number of use cases. The idea is that we transfer all these use cases together, and eventually I was going to talk about what that means to the overall business case. Chemical dosing is quite interesting because actually when we looked at the numbers, financially it was quite minimal in terms of the benefit. Well, that didn't cost that much, and so therefore there's sort of questions about financially what the benefits are. But kind of reputation thing does have the potential, if it goes wrong, to actually have a high impact. So I'm going to show you now just an example of one of the findings from the study related to chemical dosing and the benefits of having chlorine monitors distributed at a higher spatial density downstream of the dosing point, and how that can feed back into, as Alan was saying, being more proactive with how you manage your distribution system and the various aspects that are related to water quality. So here's a chlorine time series. This is Northumbrian's data dosing point, and what happened here is that your scales here between 0 and 1.4 milligrams a litre. So you can see there's a period where the chlorine concentration is really very stable, and then you have this period at the end of January and the start of February, where the chlorine data on the analyzer of dosage becomes more variable. So we've got the analyzer at the point where the chlorine is going into the water here, and it's showing some variability, but nothing of massive concern. You know, we've got variability in maybe 0.2, 0.3 whatever it is, what is short. So therefore, you might think that actually by the time it gets into the pipe and it's distributed downstream a little bit, then actually if these spikes were even now, it won't be an issue. There's not necessarily that much of an issue at this point. It looks fine. If what the water company traditionally does is in the downstream service reservoirs monitors the chlorine concentration in the reservoir with a handheld test. And so this is the downstream service reservoirs, the black dots, the chlorine reading from the downstream service reservoirs. So at this point here, we'd probably pick up, actually, it looks like this chlorine reading's gone up to above 1 milligram a litre. Maybe we should do something about it. But it's difficult because if you're a water company, you've got a vast area to cover. You'd be going up one sample that actually one person's collected from one service reservoir. So maybe you'd be struggling at that point to make a decision about whether there's wrong. Here we've got a number of chlorine monitors that are on the inlets and the outlets of the service reservoir downstream of the dosing point, and also on some DNA inlets. And what we saw within the space of a few days is actually that the chlorine concentration on all these monitors is going up, and in some of the cases to above 1. So this is here to kind of demonstrate that actually, if you've got more monitoring in place at remote points downstream of your dosing points, you can pick up these things much earlier, and you can act much more in advance to before these things get worse. And so at this point, the rig was switched off, and then the chlorine concentration drops down. So I think what was happening was the analyzer wasn't reading the right thing, so it was overdosing at the rig. But it's very hard to tell actually at the place where the dosing point was that actually there was something that was an issue. It's also really hard to tell how that actually manifests in terms of the concentration of this convention downstream. So yeah, big networks, lots and lots of things to manage. If you don't have the visibility, sometimes it's hard to pick these things up. So simple use case, but potential to really save some big issue. Alan,
I talked about this more earlier on in the intro, that this is about unlocking information, intel within a system that isn't necessarily apparent today with the techniques we have. As I say, well, we currently use verification sampling, the compliance sample, whether operational, etc., through accredited labs, etc., and the likes. We might look at customer contacts traditionally. We carry out inspection regimes and service reservoirs. That's only done in what generally, depending on which company you're in, somewhere between every 3 years to every 10 years. So the frequency is really low. And then you're almost relying on customer apathy that they don't bring in when changes occur. Just trying to kind of shift the dial on this now. And as Matt mentioned, in terms of where we got to with this project, I think we've seen real tangible and intangible benefits from it. Things that we always wanting to find out, but things that we then inferred through the information, and we saw very different things. And when you put all those numbers together, whether it's kind of a high profile kind of reduction in the impact of a big event, or it's kind of some of the subtle things that maybe John talked about at the end, what it's done is given us a completely different insight into a very large network. So much so that actually the cumulative benefits from all those elements that we've talked about, and again, there was plenty of them, which was giving you a snapshot, actually created a really easy business case to take this from a prototype actually into business as usual. So we've now actually signed a 3-year contract with Siemens to run the system as is. And actually what we're now looking to do is where is the opportunity to deploy this everywhere. It may be that it isn't a simple case where you just want a complete saturation of instruments all over the place. That isn't, it may be that you just want to target areas where you believe you've got issues or you need more insight. And I think that's the space where we're trying to work into actually what does phase 2 look like. We believe we're kind of unlocking so many of these elements, moving out from that diagnostic into the kind of more proactive asset management space. And importantly, from a customer point of view, we're starting to get a lot more control on how we do things. John's using an example there of chlorine. There was another really good one whereby the high frequency pressure sensors were downstream of a pumping station.
Do you want a couple of slides on?
All right. Yeah, all right. If you were going to cover it, I won't say
No, you do it. That was cool. Yeah.
No, but essentially what we found was that we've seen a lot of water hammer down by that. We identified it through the sensors. And actually, because we'd identified it and we found out that within the graphics program, it was a simple persistence timer. We basically changed the persistence from 30 seconds to 60 seconds or something like that, and it completely dampened the issue. Now that undoubtedly is saving kind of potential mains bursts and various other things, and it's low cost. When Killian's talking about service reservoir water aging there, you know, it may be that we're not necessarily going to change the dynamics in the reservoir, but we're using our Aqueduct program in our control room, but basically is tariff management for the water network. Or we can instruct that to do deep cycle in a reservoir to actually drop it a bit more, turn the water over. That can be done automatically. So it's not actually creating a huge operational expenditure. It's what those little tiny advantages we can get, which ultimately help those low failing assets fail even less, or give us the confidence to know that we're on top of those issues. So they're the sort of things that we're seeing through it. It isn't just the big scale stuff like it's an event. And actually, just kind of relating to that story Matt told about those events. You know, traditionally, when we're looking at time of travel, when we're in event management, we'd use our hydraulic models to understand how long the water will take to go from A to B. Our models in that said it would go from the location of the source of the event to Middlesbrough in 2 days. Actually, 3 independent DMAs all spiked in a very small way, 24 hours earlier, all spiked independently, just with a tiny surge to the tail of that event, just and a minor blip on stability. But basically, we'd have turned up 24 hours too late if we would have relied on the historical methods. This just gives us a very different insight to how a network works. So I think that in itself is kind of really powerful. Okay, John, back to yourself.
Thanks, Alan. That's great. Yeah, just to talk a little bit about horizon scanning and future innovation and where it might go to next, really. So Alan touched on this one, so I won't cover it again. But essentially, there's a number of other emerging use cases to be found we tried to present the key ones in terms of what got fed into the business case, but there's loads of, like Alan says, there's loads of little bits you just find here and there. Oh, that's interesting. That's interesting. What that might mean, that, these kind of things. And I suppose that's the point really. It's about, that's the benefit of the sensor network that's got multi-parameters on it, right? You can start to actually characterize how the system behaves, understand the assets in more detail, and there's loads of stuff that comes out when you start monitoring these systems that you wouldn't know or wouldn't necessarily think were going to be a key part of the business case, actually. So it's been a really interesting learning journey, as much as it has been a commercial success, I'd say. And so some of those, and so I'll just touch on this one here, that we had a kind of tracking the projects to look at leakage and the synergy with water quality. So here's a nice example from the DNA where we had 3 instruments deployed at DNA 1, 2, and 3, and then the inlets here basically at this point here. And what we were doing is using this transit time algorithm that essentially, I don't know if you can see this very well, but you can see on this conductivity time series, maybe you can see it, I don't know. But there's loads of little ripples that happen and loads of like little distinct features in the time series that it's happening on these 4 sets of time series that are basically the inlet and then DMA 1, 2, and 3. And so what the algorithm does is it basically uses that to basically look for the lifetime between these features so that it can extract out the water age. And Killian talks about that a little bit on the service reservoirs as well. So the point here is it applies to a service reservoir, but you can also apply it into the network and use the same technique. And so what we were looking at is, obviously, nobody really wants any leakage, but in some ways the benefits of leakage are that it reduces the age of the water. So in some ways that's a win. So that's a controversial thing to say. But so it's not just as simple as let's just drive all the leakage down, because if you did, then actually you increase the water age of the system, and actually we don't know what the response to that would be. So one benefit of this algorithm is you can start to see, well, when you get a leak, how does that change the water age? If you fix a leak, how does that change the water age? I'm not saying you necessarily not fix the leak, but it's nice to know before you actually do what the impact's going to be. So the very simple and short version of this is conductivity data across a few places, extract out the age and the transit time, understand what the age of the water is before the leak starts and after the leak starts, and maybe what we can do if we have density deployment of conductivity sensors is use that in some way to actually work out where the leak is positioned in the cycle behind. So, what kind of instrument is pressure or flow, and schools have lots of success with temperature measurements for leak detection. Maybe conductivity might also play a role. Is it going to dual validate actually when the leak in the system? So, one example needs developing further. I think it's got some potential. Right, and then so next thing is Horizon Scanning Report. So the guys at the University of Sheffield worked on this as one of their tracks inside the project. And so there's various things that came out of that report. If you would like a copy of the report, then please contact colleagues at the University of Sheffield. I'm sure they'll be keen to share that with you. Some of the big things that they picked out were key advances might be around, it's a continuum. So we've got to the point now where the stability instruments are working well enough that we can detect these big changes in the system. We've got some algorithms that interpret the data and standardize the data so we can look at a material movement above a certain baseline. But maybe in the end, what you want is you always want them to be better. So perhaps because we also, in order to understand exactly how much material is moving through the system and what the sources of the things are, can we continue to work on improving the performance of stability sensors? Chlorine monitoring is still a bit of a pain. It's probably one of the key contributors towards the confident deploying and managing and maintaining the sensor network. So on the next slide, I'll show you an example of something else we've been looking at on the chlorine monitoring side. And then, wouldn't it be great if we could have some more organism-specific microbiological sensors, and that, there's various things that are coming through on that front. And then I think one of the other key points around comms, power, and analytics. Where you do the analytics, you don't do it on the edge, you do it on the central repository, all those types of things. And I'm sure Jody and Killian can give you a much bigger, more detailed view of that. So, please feel free to reach out to the guys to understand a little bit more about the direction of travel of technology. And so, yeah, as one example, we've been looking at a technology from the US. It was developed for ballast water disinfection control for the US Navy. This company called Halogen. I think the big innovation here is that it cleans itself, and it also has an impeller so that it doesn't have to be, you don't have to have a flow for the chlorine test, right? It also doesn't have a membrane, so there's less likelihood of it actually fouling. So currently they've been working with the sensor supplier Salamander to put this together as a low power system that we can deploy and trial in Northumbrian. I think we're at the point where they're trialing it and it's working in the factory. Next step is to actually get it in the field and compare it against the traditional technology, membrane technology. But the main point here is about this, we're trying to get continuing. It's about continuing to work on this. Technology evolves, and we need to make the project evolve with it and give the industry the best and the most cost-effective solution.
Any questions? Anybody want to ask any questions?
What's the time on
the kind of technology has been in the market for the last 20, 30 years. And so they've worked fine on the treatment works because you've always got a manual there that get calibrated once a week. Probably where we're up to in terms of these ones is needing to go on average once every 3 months for a tweak, and then once every year for a electrolyte replacement and a membrane cap replacement. Yes. The halogen one's more expensive, but the idea is that actually it saved absolutely tons on the maintenance side. So it probably adds up. And I think it's probably worth saying on that actually that the thing that we didn't do on this project that we thought we might be able to do is look at the different decay rates across different parts of the network and use that to actually see whether you've got particular hotspots of the network that are contributing more towards decay than others. We didn't get the sufficient precision of the measurements really to get down to that detail. So we found it was good. The current chlorine monitoring is good for picking up those big changes, like I showed on that example. But actually, we've got some hopes that actually the halogen one can start to get into, tagged sections of the network that actually are more aggressive in terms of chlorine decay rates and things like that.
So this is moving into BAU now. We're putting monitors everywhere, right? All over, like.
VAU is primarily this system.
Right, so it's still focused on one system rather than
at this moment in time. Yeah. I mean, so I think it was mentioned earlier in the presentation. One of the things that's helping is what we're trying to optimise as we go through the programme is even things like battery life. You know, we started at around 3 months, didn't we? And now we're pushing that to 11 to 12 months. I mean, that's a significant, advantage when you're trying to maintain this. The other thing I would say is the in-service, as a service model. There's, without kind of throwing Northumbrian water under a bus, and I'm sure we're not unique, if we had to maintain these instruments, it would only be a matter of time before one would be missed and then the second one would be missed. Actually, I think that's kind of the penny drop moment internally, and I think it's the game changer to get that level of data confidence really on a day-to-day basis.
Yeah, that's going to be critical, and particularly for the first use case, because as Matt was saying, it's really, these are high impact events, but they don't really happen very often, they're very low frequency. So, the system's there as an assurance for like when it does happen, you need to be able to intervene. Well, it's not going to work if the kit's not maintained. So yeah. So business model is key because it means that over the time frame you're keeping it up, keeping it available. It's pretty for making the intervention.
It's really interesting. And it's like the first step towards no longer filling bottles, which is just a way to manage water quality. Did you manage to get DWA interested? And what then offer their view?
Yes. Yeah. We actually we've had a number of follow-up design sprints at the Innovation Festival, and not the most recent one, the one before actually Marcus Ring came to the tent and actually spoke and was fairly complimentary that this is the direction to travel, which was good. And I think he also liked the fact that we were trying to think synergistically, basically, and not just looking at solely blinkered view of water quality. It's what else we could infer from that and extending the sensor technology.
Have you been able to use it in event?
Yes. Even this week we've used it in a compliance report. Yeah, because and again, I know it's kind of more in that reactive space, but we had a metals fail in a customer tap in Redcar, and actually through a spike in turbidity in the DMA, we're actually linking it through to a third party using the stamp pipe. Yeah.
You mentioned that it's a cumulative effect of lots of small gains, and it's great that you've managed to make the business case for BAU. What do you think is the biggest barrier that others would have to convince their organisations to take this on board?
Good question.
I don't think there are any. Everyone should.
There shouldn't be. No. I don't think it's any different to what we talked about this morning. It's behavioural change and sort of it. You know, it's because you're talking about, generally speaking, low failing assets. It's selling what this actually offers, I would suggest, because it's a commitment, yeah. But ultimately, I think if we're kind of looking at a long-term strategy around customer service, this is the space you need to go. I think Katrina's just asked, do we just rely on customer contacts? Do we just rely on 100 ml sample bottle taken every few days? Or do you do real time? I think that's the future. That's the direction we need to take. But that's a really hard sell, because actually you could go months and not actually find anything. But it's that golden nugget that does come through and you'd be able to react to it. That's the key thing.
At the moment, you have to pay twice because you still have to deregulate for DWI and wayfair. Do this.
Yeah.
I don't think it'll replace it anyway, though.
You know.
Can't see it, not for a long time.
Just maybe do less operational monitoring.
Yeah,
rather than compliance.
Yeah. Good.
Just an analogy there, 4 years ago, you probably work paid recorders and put them on to measure pressures, and now we have permanent pressure monitoring fed back through their rollers. We done it for flow and pressure.
Yeah.
Can you just be clear how it's installed in the distribution system?
It's flexible, so normally with a.
John, can you just repeat the question because it's quite quiet?
Question was, how do you install your equipment, basically? So it's a very simple install. It's a flexible, quick fit. Fits in quite well with a pressure monitor. In a DMA chamber, you just tap it into it's just connected directly into the tapping on the main, or you can fit it onto with a hydrant cap into a hydrant.
When you fit it into a hydrant cap, how do you do that? Is it just on the top of the hydrant?
No, so it sits anywhere around the hydrant with a cap and a weight.
Yes, to take a sample of water out of the standpoint.
Yeah, so the way that this particular instrument works is it measures the pressure, and then it basically says at that pressure, I need to purge 6 litres to clear the interconnected pipework, so I can take a sample from the main. So I know I need to purge for this time frame at that pressure in order to purge 6 litres, and then it analyses the resultant sample at the end of the purge sequence. So when Matt put the slide up, the advantage is that you get accurate time stamping because you're actually tagging the timestamp to the water that's moving in the main, rather than it just bleeding out of the main past the sensor in a continuous flow. So that makes sense.
Can you set, probably down conversation, one-to-one conversation, but can you set the time that takes that sample?
Yeah. So it's on 15 minutes. Actually, what we've been working in as part of the alarming process for the use case 1 is that really what will be advantageous is that when an event's happening, it increases the frequency of the logging and the.
So it takes a sample every 15 minutes?
Yeah, and the batch will last 5 years. Yeah, so as a valve, we're basically opens. And then we'll do it again. Yeah.
Did you select the DMA to trial this technology?
It's actually about 50 DMAs in total. Is it 50 or 30? I can't remember. Yeah.
Yeah, it was 50. There was only about 20 we put the kind of leaks.
Yeah.
Finished off like 50 in the system.
Yeah, so it's not a single DMA.
Oh, okay.
It's a supply area.
Right. Okay.
Yeah.
Yeah, and we kind of had a phased approach, didn't we? So initially we had a project that was monitoring the service revenues. So I think that's an outlets. That's very straightforward.
Well, it was strategic network. That's essentially what and what we're trying to do is, I think the initial question was, how do we understand if a service reservoir is a single source of material? That was, but then we kind of extended it to say, well, actually, if we put sensors on the inlet and outlet of a service reservoir, not only do we understand the dynamics within the tank, but we can also start to understand the dynamics in the pipes between tanks. And essentially, that's where it was born from. And then I think where we brought Ofwat innovation in was to say, actually, if we really want to do it correctly, we need to get into the DMAs, and that was the extension. Yeah.
Often found the barrier to doing like this is the inlet. An inlet sample comes from the surface reservoirs because when you've got outlets, you have to have them installable with.
Majority had the access, didn't they?
Yeah, we didn't. So there is a few.
That's a real barrier for us. Yeah, the inlet.
Yeah, there was a few where we couldn't get on the inlet.
Yeah.
Yeah, candidly.
And they're deep, and it just end up with a lot of upfront costs just to get that inlet sample improved.
Yeah, and then you get down to, well, is some monitoring, you know, even if you could just get on the outlets, is that better than nothing anyway?
We really could the inlet and outlets.
No, absolutely. And so we took the approach here where, as an example, there was one res where we could get on the inlet, but we couldn't get immediately on the outlet. But actually, like 2 miles down the main, there was an access point of the on the trunk main, and so actually the water age calculation for that res, it's slightly overestimated because it's also got some pipework included. But you kind of get into these conversations about like you can't have it. It's never going to be perfect, so you have to take some sacrifices somewhere, and then essentially it is about individual assets and understanding them. But I think a big thing about this was that you've got sufficient coverage that you can actually understand broadly how that control group functions and behaves. Alan was saying really interesting stuff about there's an event up at the head of the system and there's a discoloration pulse coming through that gets really high in the first res, and then actually down at the pump station, 20 miles across to the east, see these little pulses that get to about 0.5 NTU. And so you start to understand about transit time, how much deposits, how we mobilise, all that stuff that you just, you think kind of happens, but until you see it, you can't say for sure, So, yeah, they're thinking. So, yeah, there's definitely some sacrifices here and there. Yeah. Can't do that, so we'll do this.
I'll do one. Has it led to any changes in decisions around asset renewal or replacement, so like reservoirs, mains, anything around that like that? That's obviously the reactive sort of benefits of it and resource management. Has it changed any of your decisions on asset investment? I guess
not directly at the moment. I think we alluded to it in the presentation. We do pipeline management, mains conditioning to try and manage discoloration. Instead of having like a ubiquitous program, we've been able to focus in on very specific pipelines where we need to condition. So from an asset management point of view, that then optimizes that approach.
So does it reduce the length you're having to flush essentially? Are we talking?
Well, yeah. I mean, we're more diagnostic at the moment, but because we're now starting to get that appreciation of the material transfer, we understand where the most deposition is occurring within DMAs, and we can prioritise the flushing within those DMAs first, rather than wait for contact rates to create a prioritisation. Yeah.